Okay, so this last application we're going to look at in section 2.2 deals with the intermediate value theorem, which we can abbreviate IVTHM. Nice, easy way. So what does it say? So we got let A and B be real numbers such that A is less than B. If f is a polynomial function such that f of A is not equal to f of B, then in the interval, the closed interval from A to B, f takes on every value between f of A and f of B. What in God's green earth does that mean? Well, let's take a look at a specific case related to zeros. So one application of the intermediate value theorem is in isolating zeros of the polynomial function. If for some polynomial function f we have f of A is less than 0 and f of B is greater than 0, or vice versa, then there must exist a 0 between x equals A and x equals B. And the reason why is because what do we know about our polynomial functions? They have to be continuous. There's no jumps, there's no breaks or anything like that. It's always a smooth curve that goes through that polynomial function. So let's just draw a quick little sketch to show you what I mean. So if we have, let's focus on the first and fourth quadrant. So if we said that A was equal to this x value here, and B was this x value there, and now we have a function that has f of A less than 0. So the y value at A is less than 0, so that means it has to be somewhere down here. So this would be f of A. And then f of B is greater than 0. So let's put our point up here, and we'll call this f of B. So now we have to get somewhere, somehow, to get from this point to that point. And it doesn't matter where you look. So if you said, okay, I want to stay down here as long as I possibly can, and eventually you're going to have to start coming up, and you will have to cross someplace to get up to this point. I kind of went off track a little bit, but you get where I'm going with this. So sometime you're going to have to cross that x-axis, no matter what. Because it's continuous, because it's a continuous function, it has to cross through there. So we can use that to our advantage. Just to verify, we know there's a 0 somewhere between A and B. We don't know what it is, but we know there's one in there. So let's prove that with this example. So let's use the intermediate value theorem to show that the function has a real 0 between the two numbers given. So we have this polynomial function. Now we could go through and try to solve it and see what that 0 is, but they're claiming it belongs, or one of them at least, happens between 2 and 2.5. Well, let's see. We first need to know what those y values are at those two spots. So if we plug a 2 in to our function, and then just plug everything in, we should get something that is worthwhile to us. So 2 to the third is 8. 8 times 2 is 16. 2 to the second is 4. 4 times 8 is 32. And we can make this an 18. So it looks like if we add all that up, 18 and 16 is 34. 34 minus 32 is 2. Okay. What about f of 2.5? So this one we might have to break out our calculator. So we're plugging 2.5 in for x. And there's the plug-in. Now let's get our calculator out. We'll use a graphing calculator to make life easier for us. So let's see what we got. 2 times 2.5 to the third power. And then we want to subtract 8 times 2.5 to the second power. And then we want to add 2.5, and then we want to add 16. Let's see what we get. Negative 0.25. So negative 0.25. So one y value is positive, one y value is negative. So we know it's coming downhill through the x-axis somewhere between 2 and 2.5. So, so as far as just as a concluding statement, you know, you can kind of say something to the effect, therefore, if I have some lead here, therefore, by the intermediate value theorem, there must exist an x value between 2 and 2.5 such that f, well, let's call that x value c, such that f of c equals 0. So, so yeah, we're calling that x value c. So some x value c between 2 and 2.5 has to exist such that f of c equals 0 because it's a polynomial function. All right. Now again, you can rewrite that how you want, but that's the essence of what we're trying to say here. So, all right. So that wraps up 2.2. So see you in the next video for 2.3.